Okay, boys and girls, welcome to this new edition for my online lecture again. Okay, this time around I want to talk to you about metals. Okay, for those in my class, I believe I've gone through the topic for the physical characteristics for metals as well as the chemical properties of metals. For chemical properties of metals is quite easy. Most of it we have gone through on the topic for periodic table as well as in acids and bases, where primarily metals will react with three things. Metals will react with water, cold water, metals will react with steam, and then metals will react with acids. Now from all those three reactions, we are back to what you call we form up what is this thing called the reactivity series. Now if you look at the reactivity series basically is the order in which metals are listed according to their chemical reactivity. So if you look at here, they're all together about 16 metals, okay, and the least reactive, obviously, it's gold, silver, and copper. And then where it goes up all the way to the most reactive, where in this picture is potassium and sodium. So, of course, this reactivity series is not exhaustive. There are metals such as titanium, nickel, who is not listed here, but these are the metals that are in our syllabus. Okay, so we just stick to them. Now, if you look at these reactivity series, there's a few things that strikes out the most. Okay, but before I go into that, we'll talk about silver. Silver, of course, silver, gold, and copper. Silver and gold primarily is used for ornaments because of its low reactivity and its attractive appearance. So chances are it won't corrode in air. Now, as I was saying, the most striking thing that you can see about this reactivity series is the position of aluminium. Now, if you can recall earlier for my class, aluminium would not react with either water or steam, so suggesting it's quite low in the reactivity series. However, if you look at the reactivity series, it's number 5. Okay, so it suggests that actually it has an adverse effect. It's quite reactive. So what is happening here? This is quite an important thing to remember when it comes to aluminium, so please pay attention to this part. Aluminium is actually, when it's exposed to air, it's actually covered with a thin layer of aluminium oxide. So basically, when you exposing aluminium to air in general, it will react with oxygen in the air and you will form Al2O3, which is aluminium oxide. Now the problem with aluminium oxide is it coats the aluminium metal and it prevents the metal from reacting. So you have aluminium oxide when it comes into contact with water or steam, okay, then nothing happens to it because aluminium oxide does not react with water or steam. So what happens if this oxide layer is then removed? Then your aluminium would then react as per normal. Now what happens if the aluminium oxide is exposed to, let's say, for example, acid? Now, if you can recall, backtrack, to the topic on bases. Okay, aluminium oxide is an amphoteric oxide. So if it's an amphoteric oxide, it will act as either a base or an acid. So it will still react with the acid. So no problem if it's exposed, if it comes into contact with acids. But the problem here lies if it comes into contact with water or steam. So when aluminium comes into contact with water or steam, it does not react with either. Okay, because of that layer of aluminum oxide. So this is fairly important, kids. You need to know about this factor. Now, also if you look at the reactivity series, you can see that actually hydrogen is placed in the reactivity series. Now, this is quite ironic because hydrogen is not a metal per se, but why is it placed here? Because it is the only non-metal that has a metallic property. Okay, so if you can recall, hydrogen can form a positive charge ion, okay, which is similar to some of the group 1 metals, and it's quite reactive. Okay, so why do we place here besides the fact that it is a non-metal? Okay, so we actually use it because of its characteristics, and it is actually placed in between lead and copper. So it is used like a benchmark per se. Any metals that is below hydrogen would not appear to react with acids to form hydrogen gas. Okay, so that's why copper, silver, and gold does not react with dilute HCl. So we use hydrogen sort of as a benchmark, okay, for unreactivity. Now, so reactivity series can be used to predict what chemical reactions, if any, will happen. Okay, so for example, gold is below copper. So since copper does not react with water under any condition, you can assume that gold does not react, okay, in any way, because it is definitely less reactive than copper. Okay, so the reactivity series also is very important in the extraction of metals and the prevention of what do you call this? Oops, sorry about that. It is used in the prevention of rusting. So we'll look into that later on. Now, an explanation for the metal reactivity series. When metals react with water or dilute hydrochloric acid or any other acid, the metal atoms will lose electrons to become ions. So they will form positive charge ions. Okay, this one you all know it in the topic on atomic structure. So the more readily a metal gives up its electrons to form ions, the more reactive it is. So it basically means that the reactivity series is also a measure of how readily a metal gives up electrons to form positive ions. So for example, if you were to look at sodium, sodium is always dying to give up its electrons as compared to, let's say, copper. Copper is very reluctant to give up its valence electrons. That's why it is very less reactive. Okay, so an explanation for the reactivity series: a metal high up in the reactivity series would react vigorously with the chemicals, rarely give up electrons to form positive charge ions, corrodes easily in water, air, and moisture. A metal low down in the reactivity series would have the adverse effect: does not react vigorously with chemicals, does not really give up electrons, and does not corrode easily. Okay, so you can safely assume that the reactivity of a group 1 and group 2 metals increases down the group. Across the period from right to left, okay, the reactivity of metals also increases. Okay, so this is how it goes. Alright, in general, okay, that's what I'm talking about. Alright, okay, so that's that for reactivity series. We are now going to the more important parts of the metals parts, the applications of the reactivity series. Now let's talk about displacement of metals. As I inform my class, whenever you see displacement reaction, you can safely assume that usually one is more reactive than the other. So the last time you see the word displacement reaction, usually the halogens, the group 7 elements, are the one that undergoes displacement reactions. Why? Because one halogen is more reactive than the other. So for metals, it goes the same as well. If one metal is more reactive than the other, then it can undergo displacement reaction as well. So as I was saying, displacement reaction basically means one metal can displace another metal from a compound. So we will look at two kinds of displacement reactions. One, displacement of metals from solutions. Number two, displacement of metals from metal oxides. Now what do we mean by that? Now let's take a look at displacement of metals from solution. Now let's have a zinc metal and copper 2 sulfate solution. Now if you can recall, I think you all did a practical on this. Zinc metal is grey in color, copper 2 sulfate solution is blue solution in color. So when you place a piece of zinc in a copper 2 sulfate solution, what actually transpires is the brown solid forms on the surface of the zinc and the blue solution becomes colorless. Now what is actually happening? Okay, so basically I can't possibly play the flash program, so I have to apologize because of that, but let's just assume. Basically what it means is this: when the zinc is placed inside copper 2 sulfate, which one is more reactive? Obviously here you compare the zinc and the copper, because zinc and copper are metals, right? So zinc is more reactive than copper, so what will happen is zinc sulfate will form in copper metal. Okay, so as I was saying, displacement reaction, it works generally the same for all types of displacement reaction. A more reactive metal will displace the ions of any less reactive metal. Okay, so for example, just now as I was saying, what would the chemical equation look like? It looks like this: zinc metal plus copper sulfate. Then let's say if I were to draw something here, the zinc would kick out the copper, and then after that it will form the zinc sulfate, okay, and the copper metal. So what you will see here is this. The copper metal will be brown in color, and then the zinc sulfate is colorless. Okay, no color. Okay, so that's basically how it works. Alright, so basically the zinc will displace the copper from copper 2 sulfate solution because the zinc is more reactive than copper, and basically this is the half equation, the ionic equation that you will see, and then you will get transferred to the copper metal. Okay, now more importantly for displacement reaction, okay, people usually generally get the products right, but they don't get the observation correct in the first place. So you need to get used to what is the color form, what is the color of the solution, what is the color of the metal, and so on and so forth. Alright, so the displacement of metals from solution can be used to find the position of metals in the reactivity series. So let's do a bit of thinking time here. Alright, so for now, okay, you can pause and you can just try and hazard a guess. I give you about 5 minutes. Pause for 5 minutes. Okay, so now I hope you are done. Okay, let's discuss the answers. For part A, iron plus copper 2 sulfate. Now in this case, iron and copper, which one is more reactive? Obviously it's iron. So iron plus copper 2 sulfate will form iron 2 sulfate and copper metal. Okay, now for part B, tin and magnesium sulfate. Is tin more reactive than magnesium? The answer is no. So you won't see any reaction taking place. C, copper plus tin 2 chloride. What do you think? Now, even though tin is not part of the reactivity series, you should hazard against it. If you compare copper and tin, obviously copper is the least reactive. So obviously, copper metal will not be able to displace tin, and so there is no reaction. Last one, magnesium plus tin 2 chloride. Magnesium is one of the more reactive metals, so it will displace tin to form magnesium chloride and tin metal. So in this case, which of the following mixtures will react? A and D. So give yourself a pat in the back if you are able to answer these questions. Alright, part 2, displacement of metals from metal oxide. Now, displacement of metals from metal oxides works roughly the same as the previous one. So basically, a metal will take the oxygen from the oxide of any metal below in the reactivity series. So instead of the solution, the anion, in this example, it will be the oxide. So it still works the same. So for example, magnesium plus copper 2 oxide. Okay, since magnesium is more reactive than copper, okay, more reactive than the copper, then so it will displace of the copper and you form magnesium and magnesium oxide and the copper metal. So that's about it. It's easy peasy. Okay, so the magnesium will give up electrons more readily than the copper, and then this is what you call an example of this is what you call a thermit reaction or a thermal reaction because of the great amount of heat produced. Alright, so this is how it basically works. Can't show you the flash because my iPad doesn't support flash, so it's okay. Just imagine. Thermit reaction of aluminum powder with powdered iron trioxide is used to produce molten iron to weld railway lines together. So basically, sometimes railway lines have some gaps, right? So you need to close up the gap. So what you do is you add aluminum powder to iron trioxide, then it will produce the molten iron, so which will fill up the gap. Okay, that's about it. Simple. Alright, so let's take about 2 minutes to answer this. Now hit the pause button, and after we'll go through the answers. Alright, welcome back. So now let's discuss the answers. Calcium plus iron trioxide. Is calcium more reactive than iron? Yes, it is. So it will form calcium oxide plus molten iron. Then after that, zinc plus silver oxide. Is zinc more reactive than silver? Yes, it is. So it forms zinc oxide plus silver metal. C, zinc plus magnesium oxide. Is zinc more reactive than magnesium? No, I don't think so. So there's no reaction there. D, iron plus copper 2 oxide. Is iron more reactive than copper? Yes, it is. So iron will displace copper 2 oxide to form iron 2 or 3 oxide and copper metal. Alright, so that's about it. Now, let's talk about carbon. Now, reaction of metal oxides with carbon. Later on, we'll talk about the blast furnace reaction, and you'll see that this is actually quite important. Now, carbon can remove oxygen from the oxides of metals that are not too high up in the reactivity series. Now, for example, let's say for example copper 2 oxide plus carbon. What carbon can do, carbon can steal the oxygen away to form carbon dioxide and copper metal. So the carbon actually removed the oxygen from copper 2 oxide when heated together. So basically in this reaction, the carbon actually is considered like a metal per se, okay, which is quite strange because carbon is obviously not a metal. So basically, the lower the position of a metal in the reactivity series, the easier it is for carbon to remove oxygen from the metal oxide. Alright, so where is it that we actually draw the line? Which oxide, which metal oxide does the carbon not able to steal away? Basically, let's say for example, okay, this is very important. Usually the carbon is not able to displace, okay, metals that are in the top 5 reactivity series. So for example, sodium, potassium, aluminium, magnesium and calcium definitely cannot be decomposed or cannot be reacted with carbon to remove the oxygen. Okay, so kids, remember this: top 5 metals, carbon cannot remove oxygen from the oxides of these metals. Okay, top 5. The rest all can. Okay, now let's talk about reaction of metal oxides with hydrogen. Hydrogen too can remove oxygen from metallic oxides, but it will produce metal and water. Now how does it goes? So for example, lead oxide plus hydrogen, okay, hydrogen can steal the oxygen away from lead to form water and lead metal. So the lower the position of a metal in the reactivity series, the easier it is for hydrogen to remove oxygen from the metal oxide. So same thing also, if let's say hydrogen is in the, what do you call this? Basically, if let's say if it's in the top 5, there's definitely no way for the hydrogen to steal the metal away. Now, some of you will recall, hydrogen is part of the reactivity series. How can it be possible? Hydrogen is placed below lead. But this is one of those things that actually happen. Okay, so please disregard the reactivity series on this part. Okay, but hydrogen usually is less asked in exam questions. So maybe this one is a FYI kind of basis. Alright. Now, heat on metal carbonates. Basically, most carbonates decompose when heated strongly. So for example, when they decompose, basically you just take a metal oxide, you heat it very strongly, and then without any other reactants, so basically you'll form a metal oxide and a carbon dioxide gas. So for example, copper 2 carbonate, it will decompose very heavily to form copper oxide and carbon dioxide gas. So the lower the position of a metal in the reactivity series, the more easily the metal carbonate decomposes. So you just take it as it is. Basically, if let's say a metal is, oops, sorry, did I touch anything wrong? I need to pause here for a while. Okay. Technical glitch. Alright, and now back in business. Okay, so as I was saying, okay, if let's say a metal that is very high up in the reactivity series, when it forms a compound, it's very difficult to extract it or split it apart. Okay, so only metals that are lower in the reactivity series, then you can react it with carbon, hydrogen, then you can undergo a reaction because it's easier to split it apart. For decomposition as well, when you heat it up very strongly, metals that are lower in the reactivity series will decompose to form an oxide and a carbon dioxide gas. Okay, so which are the ones that cannot undergo decomposition? Okay, on heat, okay, this one again, top 5 metals. Okay, top 5 metals virtually are so attached to their anion, it can't be split apart. Alright, so that's about it. Okay, so far we've gone through basically displacement reaction, 2 types of displacement reaction, one from metal with a metal solution, then one from metal with metal oxide, then we undergo through decomposition of carbon. Okay, that's about it. Now let's talk about rusting. Okay, rusting is a very a very misunderstood concept. Now, corrosion of iron and steel is called rusting. So basically, rusting is a form of corrosion. Now, some of you probably think, oh, isn't rusting corrosion, corrosion rusting? Let's put it this way. Rusting is a form of corrosion. Corrosion is what happens when the metal reacts with anything on the atmosphere. Okay? So, for example, in this case, rusting is a form of corrosion. Corrosion is not the other way around. Okay? So, for example, okay, there's a huge picture of a corrosion of a ship. Basically, rusting is the brown solid product, okay, that is called rust. So, this rust basically has a chemical name. It's actually a mainly hydrated iron 3 oxide. So, it's Fe2O3 dot XH2O. Now, what does this X basically mean? This X is just means integer. It just means any integer, any amount of number. It just basically means the amount of water in the rust. So it varies. So that's why scientists place an X there. Now, you don't need to take into account what is that X. You just have to place that X over there. Alright. So conditions for rusting basically, it needs air and water. That's it. About it. Okay. So if it contains water but no air, contains air but no water, okay, it definitely won't rust. Okay. So other factors also can speed up rusting, such as dissolved salt. Okay, I just wanted to go through about this. If it contains water but no air, okay, most likely it won't rust. Okay, so I was saying A, B, and C also contributes to rusting, but to a lesser A and B to a lesser degree. Okay, C obviously that's the full-blown requirements for rusting. Now, as I was saying, other factors also can speed up rusting, such as dissolved salt. Okay, so for example, iron near the sea rusts faster as water on the iron surface contains dissolved salt. So for example, iron plus air plus water, then you get rust. Okay. Now, so let's explain the following. Little rusting occurs in the Sahara Desert. Iron objects rust easily in water. Iron will not rust on the moon. So let's take 5 minutes, pause for a while, think about how do you answer these questions. Okay, 5 minutes is up. Now, little rusting occurs in the Sahara Desert. Why is that happening? Because in the desert, is there a lot of moisture? The answer is no. Very little humidity. Sahara Desert is very dry, so definitely rusting occurs in the presence of water. So lack of water means little or no rusting. Now, iron objects rust easily in water. Yes, that's true, because the humidity level for Singapore is very high. You have a lot of water, you have a lot of oxygen, so chances are rusting will occur. 3. Iron will not rust on the moon. For now, okay, definitely nothing on the moon, no air, no water, definitely there won't be any rusting. Okay, so you can send space shuttle metal components in the moon, no rust will happen. Now, how do you prevent rusting? 3 general types of protection. Number 1, surface protection, very easy. Number 2, sacrificial protection. And number 3, use of stainless steel. So what are these things? Surface protection, basically, the surface of an object is covered with a layer of substance. For example, paint. Okay, you paint it with a coat of paint, obviously. Oil or grease. So usually these kind of things are those that are moving parts. So usually you oil it or grease it. You put plastic such as metal clips, your metal paper clips, or you put metal plating. You place another metal to coat it, like your food cans. Alright, so the layer, this extra layer of protection actually stops the air and water from reaching the iron and steel underneath. Now, the problem with all this surface protection is, what if, let's say, there is a scratch, and that's it. Your surface protection will not happen anymore. Now, sacrificial protection is slightly different. Now, people always confuse sacrificial protection and surface protection. Now, what is sacrificial protection actually? Sacrificial protection is actually when iron is covered by a more reactive metal. So, when it is covered by a more reactive metal, little or no rusting occurs. Now, why is that? Because the more reactive metal will react with oxygen and water instead of the iron. So, basically, it is very greedy. It will react first. It becomes more kiasu. So the more reactive metal is then used up. Now once the more reactive metal is used up, then after it will get into the iron. So what you're trying to say is the more reactive metal is sacrificed to protect the iron. Okay, so a metal that is less reactive than iron actually you are very gundu and you actually use a less reactive metal, then you will actually increase the speed of rusting of iron. Why? Because the iron will then rush out to the atmosphere and actually rust it. Okay. So for example, for sacrificial protection, usually you will use a more reactive metal. Usually you will use either zinc or sometimes magnesium. Alright. Now, why is it that you cannot use potassium or sodium? Okay. Now, if you use potassium or sodium, then it will be very reactive. Okay. Then after that, it might just not be safe at all. So usually you use a metal that is more reactive but to a lesser degree. Okay. So that's how sacrificial protection works. Now, applications of sacrificial protection. Basically, sacrificial protection is like galvanized iron. Now, galvanized iron is what most of our steel products are done. Basically, galvanized iron is steel coated with zinc. The zinc will protect the iron by corroding in place of iron. Okay, protecting ships. So, for example, your ships usually because the hull of the ships, the base of the ships are basically steel. So usually you attach blocks of zinc attached to steel hulls and they will corrode instead of the steel. Quite cool, huh? Okay, so basically once the zinc blocks are being used up, then after that, that's it, no more. Then you have to replace the zinc metals to minimize the corrosion of the steel hulls. Now another one is underground steel pipes. You know, underground there's the soil, there's moisture and there's oxygen inside. Basically you want to prevent the steel pipes from being corroded, you place blocks of magnesium scrap metal attached to the pipes. Okay, so the magnesium protects the pipeline by corroding in place of the steel. Okay, so uses of the last one, uses of stainless steel. Now you know that a lot of our cutlery, okay, a lot of our instruments are made up of stainless steel. Stainless steel is basically an alloy of iron containing chromium or nickel. Now it does not rust easily, and basically using stainless steel is the most expensive way to prevent rusting, as chromium and nickel are more expensive than iron. Okay, so used for utensils, medical instruments, for hospital operations and kitchen sinks. So that's about it for rusting. So you can just recap through the chapter. Alright, so I've gone through for the past 27 minutes. Basically, I've gone through reactivity series, a bit of reactivity series. Then I've gone through a bit about the applications of reactivity series, basically how a displacement reaction of metals work like, decomposition of metals, which metals can undergo decomposition, which one cannot. And then after that, lastly, I went through the part on rusting. So make sure you try to go through these chapters first, this part of these metals topics. The next part I'm going to attach is basically a video from last year, which is on blast furnace. That one is more content heavy, and basically I'll leave it up to you. So basically I'll leave you, I will upload 3 videos that you have to watch. One on metals, okay, for those not in my class, okay, 3I and 3J, okay, take a look at that before. Make sure you look at that video lecture first before you go through this. If you're not, then I make sure you go through and revisit that video. Then after this video, after you've watched this video, please take a look on the topic on blast furnace. Okay, so next year we will test you guys on those concepts on metals, which is quite a major topic. And then after that, then we'll see how it goes. Thank you so much. Have a good holiday. Okay, see y'all.